presentation.
Great. Thank you, Tiffany. Morning, everyone. Thanks for joining us. My name is Chris Pascoe, I'm Associate Professor at the Department of Physiology and Pathophysiology, joined by my colleague, Dr. Andrew Halayko, Professor in the department. We're going to walk you through some of the information around air quality, the impact of wildfire smoke, but also other occupational exposures that influence air quality, both outside and indoors, how they influence your lung health, and also some of the mitigation strategies you may be able to employ to try to reduce your risk. So this is a quick outline for the presentation today. We'll talk about what air quality is, outdoor versus indoor air quality, how we measure it and what influences it, and then what are some of the components that we need to be concerned about, not just particulate matter that we experienced last summer, but also other pollutants. What are some of the health effects of poor air quality, specifically focusing on the lung, although recognizing it's more than just lung health that's impacted, some prevention opportunities, and then we'll go through some research opportunities we have with the new research capacity we're building. So air quality, simply put, is a measure of the number of pollutants in the air, and it indicates how clean or polluted the air we breathe in is. Generally, Canadian cities have clean air. So you can see this picture of Winnipeg here on the left, and a picture of, I think, what most people think of as a more polluted city in China. But as I think we were all aware of, last summer we experienced some pretty bad air quality ourselves with persistent wildfires, making Winnipeg's air some of the dirtiest in the world at the time. And my colleague and I spent a fair amount of time trying to explain, well, what are the health effects of that? Air quality can be impacted by a number of different pollutants within the air. We're concerned about ozone, nitrogen dioxide, sulfur dioxides, particulate matter, which often comes from fires that are burning. We categorize these particulate matters into different sizes. So two terms you'll likely hear are PM2.5 and PM10. And I'll get into that a bit later, but that's just the size of the particulate that's in the air, which dictates how much, when you breathe it in, gets deposited into your lungs. As well, dust, heavy metals, plastic pollution in the air can all contribute to poor air quality. This figure over here, you can kind of see all the different sources. There's natural sources for a lot of this, wildfires, volcanoes, lightning strikes. Cities obviously contribute. Production of many of the materials we need contribute to air pollution and air quality. Transport, both the airplanes, cars, and trucks, but also the breakdown materials from some of those vehicles. So tires and brakes on cars will also contribute to poor air quality, specifically around cities and busy roads. It's important to also acknowledge that indoor air quality is an important thing to consider. We spend, I think somebody was saying 90% of our time indoors. 90% of people spend their time inside. So monitoring indoor air quality is also important. Everything that's outside can make its way inside. So you want filtration in place. Indoor air quality can also be compromised by volatile organics released from manufacturing, carbon dioxide with improper ventilation, as well as formaldehyde from various materials in our homes. And various agencies will set air quality standards. The WHO, the World Health Organization, as well as the Government of Canada, have set specific standards for specific pollutants that need to be tracked. So on the left here are the standards for the Canadian government. You can see they were updated in 2025, and they're scheduled to be updated again in 2030. And they set the limits for both an hourly, so in terms of particulate matter, a 24-hour time period, as well as an annual exposure. And these numbers, like, starting to decrease over time. So currently, the daily acceptable average for particulate matter is 27 micrograms per meter cubed. Annual is 8.8. And then you also have standards for ozone, NO2, and sulfur dioxide. WHO has their own standards. They do include other pollutants that the Canadian standards don't consider. And in general, they're much more strict of guidelines than the Canadian standards tend to be. But most Canadian cities, I would say, are meeting these standards, with the exception of various instances, wildfire smoke and other pollution events. So what are some of these pollutants? So we'll go through them one by one here. So nitrogen and sulfur dioxides are ones that we don't hear about as much, although when I was growing up, they were a pollutant of concern. They're part of reactive gases called sulfur oxides or nitrogen oxides, with SO2 and NO2 being the most common forms and the ones that we track um, with air quality. They're produced from burning fossil fuels, so from cars, trucks, and buses, power plants, including those that burn coal, power equipment, including those on job sites. They are the ones that contribute to the haziness of air on smoggy days. So when you look across the city and you see that haze sitting above it, called smog, that's usually NO2 and SO2. They're also the main contributor to acid rain, which, as I said, when I was growing up, was a primary concern with poor control of emissions from vehicles. This has largely become under control recently. Um, but they also contribute to the production of ozone. So a lot of these pollutants that are released from the cities, they sit in the air, and then over time, as they get exposed to sunlight, as they get exposed to UV radiation, they get oxidized further and modified, and you can make things like ozone and other more harmful pollutants. So ozone is a highly reactive gas. It's three oxygen molecules. It is a very important gas in our environment. It's present in our upper atmosphere and it blocks UV from the sun. So when we were concerned about a hole in the atmosphere forming, it was the hole in the ozone layer that was forming and it was allowing more UV light from the sun. So ozone that's up in the atmosphere is considered good ozone, but ozone that forms near the ground level and in the air we breathe is considered bad ozone, and that contributes to urban smog. And it comes from, again, those nitrogen and sulfur dioxides as they interact with heat and sunlight and produce this ozone. Um, Production of ozone tends to be worse in the summer and during heat waves and during the peak of the day. And so you'll see that there's this kind of cyclical nature to its levels where it rises during the summer and falls during the winter. But ozone is certainly one that we worry about in terms of health effects, which is known to exacerbate and worsen a lot of lung disease. And then particulate matter is the one that I think most people have experience with, especially since last summer and the wildfire seasons we've been having. Particulate matter is anything that is a suspended particle in the air. We characterize it by its size, and the smaller the diameter, the easier it is for that particulate matter to penetrate deep into your lung and even cross into your circulation. And some ultrafine particles that are smallest in the air can actually penetrate deep into your bloodstream and then circulate around your body. You can see over here a depiction of the size of these particulate matter. So this is a human hair. PM10, which is one of the things we measure, is any particulates under 10 microns in diameter, and you can fit 5 PM10 molecules across a human hair, so they're pretty small. And then PM2.5 is any particulate that's less than 2.5 microns in diameter, and you can fit 4 of these per PM10, so roughly 20 to 30 PM2.5s across a single human hair. They can be composed of all sorts of different materials, and this makes studying them complicated, and it makes understanding their health effects complicated because they don't all do the same thing. They can be organic in nature from carbon or burnt material. They can be metal. So there's a lot of brake wear down, tire and engine component wear down contributes to heavy metals in particulate matter, such as zinc and boron. They can be nitrates and nitrites. They can be sulfates. They can be dust, which we experienced, I guess it was 2 weeks ago. We had a dust storm blow through. They can also be microplastics in the environment. So these are a very diverse group of molecules, and understanding the health effects of them often comes down to more than just the number of them, but also the composition of them. It's also important to recognize that in the environment, allergens, so things that people are allergic to, ragweed, pollen, dust, dander, can adhere to these particulate matters and enter the lung, and in that way they make the particulate matter allergenic. So anybody who has seasonal allergies may experience worse seasonal allergies during high particulate loads. For example, that dust storm we had, it wasn't just dust, it was also picking up fungal spores. It was transporting allergens around, and so you may have experienced more nasal symptoms, so sneezing, runny nose, mucus production, that kind of stuff. The way we monitor these things and we try to convey the relative safety of the air you're breathing is through air quality indices. Often these are relative to some international standard, either the WHO or a government body. In Canada, the one we have access to across the country is the AQHI, which is the Air Quality Health Index. It's from the Government of Canada. It rates things on a scale of 1 to 10. You can see up here with anything in that 1 to 3 range considered low risk, 4 to 6 moderate, 7 to 10 high risk. and then 10 plus, which was added a number of years ago to convey very high, very serious risk. With this AQHI, they try to set recommendations activity for the general and at-risk populations. And so if you go to the website and you look up the air quality at any given day, it'll have recommendations for your activity, whether you're somebody who's at risk, so somebody who's young, somebody who's elderly, somebody who has chronic disease, or somebody who's otherwise healthy. You can also find information at various other websites. A lot of these are contributed by independent or private citizens who have sensors. So IQ Air is a Swiss company that monitors air quality. It presents its stuff on a scale of 0 to 500. And the nice thing about websites like this that the AQHI doesn't give you is it will give you information on the specific pollutants contributing to that score, where the AQHI is an aggregate score of the major pollutants. This one here, you can see it breaks down PM2.5, ozone, and SO2 into the specific concentrations to give you an idea of how poor the air is. The other one that's useful is AccuWeather Air Quality. It's an American company. This one has no upper end on the scale, so the numbers can just keep going up to very large values. But it also gives information on specific pollutants, as well as some breakdown of what specific pollutants do to health effects. So ozone, you can see here, can lead to worsening respiratory disease, throat irritation, headaches, and chest pain. It also gives information on NO2 and then 2.5 and 10. And so these are all metrics from Winnipeg over the last couple of weeks, showing that generally speaking, Winnipeg has decent quality air. So I'll go into a bit more detail about the AQHI, since it's the one most people will probably have experience with. It's the one that we use in Canada to convey risk. It was developed in 2008, and the idea here is it tries to present an aggregate score for three major pollutants, so ozone, NO2, and PM2.5, without any regard for which ones are driving that, just that there's an increase in the risk associated with poor air. It is constructed or built based on mortality. So it looks at how frequently people were being hospitalized and or dying in excess of normal numbers in Canada due to these three major pollutants. So it's useful in that regard, but it does and it will miss risks that are associated with things not related to death or hospitalization. So worsening of symptoms, headache, mucus production, sneezing, that kind of stuff that are more minor, although is still an inconvenience. As I said, it scales 1 to 10, bins them based on these relative thresholds, and they're all rounded. So one of the issues with the AQHI that you have to be aware of is it caps at 10 plus. And last summer, as you can see from this graphic here, this was taken on July 19th of 2025. We spent an inordinate number of days at 10 plus on this scale. And sometimes the relative risk of that number kind of loses meaning when you spend multiple days there. And you can see here was the forecasted for the next couple days and nights here. So Saturday and Sunday were forecasted to remain at that 10 plus. In this instance, this poor air quality was driven by wildfire smoke and particulate matter. And the risk was considered high, not just for those who had pre-existing conditions, but also the general population. And so to touch quickly on air quality and wildfires, after the last summer, I don't think it's any surprise to everybody, but the air quality in Winnipeg or other cities in Canada is not always great. We're seeing an increased contribution to poor air from wildfire smoke. The composition is changing. We're getting more days with these high particulate burdens and fewer days where ozone and nitrogen are concerned. Specifically in summer of 2025, I think the calculated numbers, we spent 340 hours of that summer under smoke advisories, somewhere on that scale, AQHI scale of 4 to 10. To compare, in 2021, which was another bad year in Winnipeg, although not fires in Manitoba, but fires blowing in from mostly Ontario, we only spent 242 hours under smoke advisories. So last year was very bad. This over here just shows how particulate matter changes over the course of a day. So this was June 2nd. You can see there were some periods when the wind shifted where the city was set at a good level of particulate matter, but most of the day and for long stretches of the day, we sat at very unacceptable levels. Just to give you an example here, this first dashed line is the WHO standard. The second dashed line is the Canadian standard. And so on this day from 4 a.m. till about 9 a.m., we were orders of magnitude above the Canadian standards. Um, it peaked on this day around 200 micrograms per meter cubed, which was 7 times higher than the Canadian standards, 13 times higher than WHO. AQHI was recorded at a 10 plus, but if you do the calculation and you don't round that number, the daily AQHI for that day was at almost a 19. Um, and we had multiple instances throughout June and July where we had 3 to 5 days where consecutively where AQHI was 10 plus. And so the note here is that even in wildfire smoke instances or even with general air quality, if you look back retrospectively, although the average for that day may be acceptable, you can have hours of time throughout the day where particulate matter or other pollutants are unacceptably high. So what does air pollution do to health? So this is an important study from 2018 in The Lancet, a very prestigious journal, that it estimated that exposure to pollution, predicted specifically air pollution, was the leading risk factor and cause of death worldwide. So this includes air pollution from wildfire smoke. This includes air pollution from an industry and climate change and smog. And it was estimated that about 10.2 million deaths of this total annually from the world were attributable to PM 2.5. This exceeds both tobacco smoking in terms of death, AIDS, and other infectious diseases, and alcohol use. So pollution is a big burden in the society and in the world these days. Approximately 9 in every 10 people around the world breathes air that is above the WHO standards. Now, those are pretty strict standards compared to, say, the Canadian standards, but it illustrates that the air we breathe isn't always clean, and we do need to consider the long-term consequences of this. Air pollution is also a significant driver of what we call morbidity, which is hospitalization and days lost of productivity or years lost. It affects both young children and seniors more. You can see over here in this graph by age category, the amount of morbidity, the higher the bar, the more morbidity. And those that are just born and in that 1 to 4 years suffer some of the largest burden, particularly due to air pollution in red here. And then this graph dips down, and those who are younger generally are unaffected. And then as we get older, we are also more affected. But it also affects those with chronic disease. It worsens symptoms of chronic disease. It disproportionately affects disadvantaged populations. So I'll acknowledge at the beginning we had the land acknowledgement, and so some of the populations in our country that are most affected by these are the indigenous populations, the otherwise unhoused populations in cities, those that don't have adequate ventilation in their home to escape this type of stuff. They often experience the biggest burden of this. And air pollution as a whole captures both fossil fuel emissions and wildfire concerns. And in Canada, it's the wildfire concerns that I think are top of mind for us. So particulate matter and your lung. This is an image over here of a lung. If you haven't seen it before, you've got one trachea that runs down your throat, branches into two larger airways, and you've got two lungs, a left and a right lung. And those airways branch successively into smaller and smaller airways, kind of like tree branches, and they end in what we call alveoli, which is where oxygen is dropped off into your blood and you pick up CO2 to breathe out. And we can look at how particulate matter is deposited based on its size throughout this airway tree. So very large particles, a lot of that dust we were inhaling 2 weeks ago would have been trapped in your throat and in your upper airway, which is why you probably had a sore throat. Things that are PM10, so less than 10 microns, will get into your upper airways and they'll sit in there. PM 2.5 can get into your small airways and your alveoli. That's these little grape-like clusters down here. And then things as small as PM1, so 1 micron in size, and 0.1 microns in size can actually cross your alveoli into your bloodstream. And when they cross into your bloodstream, they're now circulating throughout your body, and they're going to interact with your heart, they're going to interact with your brain, they're going to interact with your liver and digestive system. And it's important to remember that the way we define these, PM10 is any particle that's less than 10 microns in size. So that means by definition, it also includes those that are small enough to enter into your bloodstream. So just because it's PM10 doesn't mean it's only those that are 10 microns in size. Once they're in your lungs, there's immune cells called macrophages in there that go in and try to eat this particulate matter. You can see a picture over here of this is one of those macrophages, and these black dots within the cells are the particulate matter. They can't get rid of it. It kind of just accumulates and sits in there. It looks a lot like immune cells in lungs of people who've smoked chronically. They consume this stuff and it sits there, and it triggers them to release a bunch of mediators that cause inflammation and worsen disease. And eventually these cells will die because they can't handle the burden. And when they die, they recruit more immune cells in to deal with that. And so it's really this chronic exposure that becomes a problem, where you get this chronic inflammation and the worsening of health. I put this schematic up here to highlight different pollutants are associated with different health outcomes. We just talked about particulate matter, but SO2, NO2, and ozone are also concerned. So you can see that sulfur dioxides can cause headaches. They can worsen anxiety in individuals. Particulate matters, specifically those that circulate in the bloodstream, do impact your brain and central nervous system. They irritate your eyes, your nose, your throat. All of them are known to cause breathing problems, so difficulty breathing, chest tightness, wheezing, coughing. They'll irritate your lungs. They promote infections or make it harder to fight infections. They worsen asthma. They can worsen COPD. Some of them, through long-term exposure, can cause cancer. Cardiovascular disease is also exacerbated by these and worsened by them. They affect your liver and they can affect your reproductive system as well. So as I said, many of the organ systems are affected. It's not just lungs. We are talking about lungs today because we're lung biologists at heart, but realistically, the research we're doing and the concerns around air quality affect every organ system in your body. Elevated levels of air pollution also cause an increase in emergency room visits. They increase heart attacks and strokes in individuals, even those who may not be at risk for them otherwise. They can worsen lung disease, specifically asthma, COPD, pulmonary fibrosis, and long-term exposure, so continued exposure over your life course to high levels of particulate matter and air pollution in your environment will lead to the development of COPD and asthma. It can worsen or cause dementia, increase blood pressure, and contribute to your cancer risk. So some examples of hospitalizations, specifically after a wildfire event. So this was the 2023 wildfire season. This was in, I believe it was Ontario, Northern Ontario, you can see here. In this study here, they tracked particulate matter over time, and you can see there were two instances in Toronto where this study was done, where there were really high levels of particulate matter on a given day, and they were able to look back at the number of hospitalizations that occurred on those days and preceding those days, and they found that if you had asthma, and you were exposed to these high levels of air pollution and particulate matter, you had a 22% increase risk of being hospitalized. Interestingly, and of note, this doesn't happen right at the exposure. There's a lag to it. So somebody is exposed to this air pollution and they require hospitalization anywhere between 1 to 5 days after that exposure. They also saw an increase in the number of heart attacks requiring hospitalization, so 15%. And again, this was about 4 to 7 days post-exposure. And this association and the risk of hospitalization increased for every unit increase in the amount of particulate matter. Now, there was an interesting thing in this study. They noted that these risk of hospitalization only happened in that first spike, not the second spike. And they theorized that that's because people became used to living in this wildfire exposure. And so on days like this, they were seeking out shelter. They were spending more time indoors with HEPA filters. They were maybe masking up if they had to be outside. And it showed that there was a way to reduce your risk even in high level of exposure. And it's not just all doom and gloom. Should also point out that this was looking at hospitalization, but there's a lot of evidence for also mortality from these conditions, which is increasing with exposure. So just a quick note on lung disease and air quality, because I think it's important to recognize that people with lung disease are more at risk for the health effects of poor air. And as of last numbers, 1 in 6 Canadians across the country have lung disease, which means that 6.6 million people suffer from either asthma, COPD, pulmonary fibrosis, or cystic fibrosis. And what that means is you likely know somebody at your work or at your home who has one of these conditions, and they will be more negatively affected by air pollution than somebody who's otherwise healthy. And so it's important to consider the needs of those people and the risks they face when air pollution is bad. In these individuals who have chronic lung disease, exposure to air pollution and exposure to smoke will make breathing more difficult. It'll worsen inflammation, so you'll feel more chest tightness, more pain in your chest. It'll make their medications that they use to control those symptoms less effective. Some of them may need hospitalization, and unfortunately, there's evidence that some of these people will suffer more mortality from those exposures than their counterparts. So it just spent a lot of time talking about air quality in the environment, so wildfire smoke, air pollution, but it's also important to recognize that there are sources of poor air quality on job sites that need to be considered. Diesel exhaust fumes, particulate matter, and nitrogen and sulfur oxides from heavy machinery, things that burn diesel, will contribute to poor air quality on job sites. Dust production, so silica crystals is a big concern right now around cutting of engineered stone, particulate matter from cutting concrete and other materials. Demolition of excavation can also release heavy metals from the environment, fungal spores, allergens, things that can all worsen lung disease and make breathing more difficult. I'll show you some evidence just here, two studies. This is our colleague at UBC who um, has people volunteer to sit inside this plexiglass box and ride a stationary bike while they pump in diesel exhaust fumes at a level that's relative to a bad day in Beijing, or riding your bike across a very busy street or highway. They breathe that air in, and then they measure all sorts of health metrics from them. So in this study here, when they exposed them to diesel exhaust for an hour, or sorry, 2 hours, they found that in their serum, they had high levels of inflammation and specifically changes in proteins that seem to relate to risk for cardiovascular disease. So things that are involved in control of your blood pressure. And this was just after a 2 hour exposure. And luckily, this washes away. But you can imagine if you're doing this for 2 hours every single day, this adds up cumulatively. They also did a study wherein these people, they exposed them to both diesel exhaust and an allergen they were allergic to. And in that instance, they found if you did a 2 hour exposure and you exposed to both diesel and allergen at the same time, you had more airway twitchiness, which is that kind of difficulty breathing that people with asthma feel, and more airway inflammation than if you were just exposed to the allergen alone. So the diesel exhaust worsened the result of the allergen. And interestingly, for mitigation and some of the research we're looking at and are interested in, if they went to that diesel exhaust and they removed the particulate matter, but kept everything else, it didn't make it better. In fact, in some instances, it made it worse. So it suggested that the particulate matter wasn't the thing that was causing the problem. It was something else. So this is some of the research that's happening in this space. Just a quick note on engineered stone. We have a colleague in Melbourne who's very interested in this problem. Stone cutting, so engineered stone countertops and things like that, produce silica crystals that can enter into your lung. And there's increasing evidence that it causes silicosis, which is an incurable lung disease in people that causes breathlessness, fatigue, chest pain, a cough that won't go away. Often you require a lung transplant at end stage of disease. It's lethal with a median survival of 25 years, but the age of diagnosis is young. And so in Australia, where they're seeing more instances of this, the people who are cutting these engineered stone countertops without appropriate controls are seeing diagnosis as young as 39 years, 35 years of age. And so Australia has now made the step to ban engineered stone countertops in the country because of this issue. And so it's something to be aware of as another environmental risk factor. So that was a lot of talk about risk factors. And I think what will be useful now is to talk about how you might be able to mitigate some of your risk. So I've set it up these next couple of slides looking at this hierarchy of control, going from least effective but personal control to most effective elimination strategies. And we'll walk through some of the things you can do to try to minimize your exposure risk. So on the PPE, the personal protective equipment side, N95 masks are useful for filtering out particulate matter. They won't help with ozone, NO2, or SO2. But in instances where you have high particulate burden, these N95 masks and fit tested respirators can be useful. We made some recommendations last summer in the wildfires to wear these. So they're the same ones you would be wearing during COVID, and they're useful for reducing your PM 2.5 risk if you can't avoid being outside. Moving to administrative controls, it's important at the job site and then kind of in your daily life. I think as a new normal in summer in Canada is to monitor the AQHI daily, understand what the air quality index is. You can get air quality sensors. They're relatively inexpensive ones if you don't have them for the job site. You should be rotating workers to limit the amount of time they are exposed if the air quality is poor, providing them a respite area with its proper filtration with a HEPA filter so they can get inside away from that filter, that poor air quality. And then have an air quality plan for job sites. At what level is it no longer going to be acceptable to be working outside? At what level do you implement rotating shifts? At what level do you start to convey some of those risks to people working outside? A note on indoor air quality, it matters. Like I said, most people spend 90% of the time inside. Many sources of air pollution can be found indoors. Um, Outdoor air quality will also impact indoor air quality if you have improper ventilation, if you don't have a HEPA filter. And so not only is it important to have a HEPA filtered space for people to get to avoid poor quality air, it's also important that it's climate controlled. We haven't touched on it here because it's not really air quality in a classical sense, but heat stress is also a big issue. And so it's important to have a space where people can go and cool off and avoid extreme heat, because that will also not only worsen health overall, but also worsen the effects of poor air quality. There are a number of engineering controls that can be put in to mitigate some of these exposures. So a lot of these are already happening. Water suppression and misting for cutting of stone and or concrete. This reduces the amount of dust in the environment, and it's a good effective way to prevent exposure. Reduce idling on the job site to reduce the amount of particulate from diesel engines and heavy equipment, and provide filtered air shelters or HEPA filtered trailers where people can get inside away from exposures when otherwise they can't avoid work. Substitution can be difficult, and although they're most effective, they're probably the least likely to be implemented, or some of the least likely to be implemented. So replacing high emission generators with something that's more low emission, alternative fuel sources. There's some interest in biodiesel and how that might relate to air safety. Substitute outdoor work with indoor work where possible during poor air quality. If there's something that needs to be done, that can be done indoors on days where AQHI is approaching 7, 8, 9, 10, it's probably a good idea to do that. And then elimination, again, probably the most effective, but also the least easy to implement. So schedule work to avoid days where there's poor air quality, or at least times where air quality is poor. And AQHI does an all right job of forecasting what the likelihood of poor areas throughout the day. So you can look there. Have a plan in place for what AQHI thresholds are considered safe and what are considered unsafe, and then what you'll do when it reaches an unsafe threshold. And then, like I said, relocate work indoors where possible. So those are some of the prevention possibilities, while we're still trying to understand what the long-term and short-term health effects of much of this exposure is. So I'll pass off to Dr. Halayko now.
Sure. Thanks, Chris. Is my sound fine? Sounds good. Okay, great. Thanks, everyone. A pleasure to be here this morning and chat with you. And I'm going to finish off the presentation by telling you a little bit about what we're building and what we're doing here, and some opportunities for engagement in research, as well as helping us define the research directions that we might take with our planned facilities. So go ahead, Chris. Next slide. Thank you. So you've heard a lot about this from Chris. I don't need to give the details. The bottom line is we inhale a lot of things in the real world situation. This is not a new problem. There's an article here from 1912 talking about burning coal and greenhouse gas emissions, particulate matter, and its effects on climate and our health. So this is something that we need to pay attention to. And the picture to the left is actually from a colleague from 2016. And I've added two little inserts here of a couple of teenagers vaping, as well as wildfire smoke. So in the time that this wonderful article was published 20 years ago, we've got two additions to this. And the take home I want you to get from this is that when we are exposed to pollutants, we aren't exposed to them in isolation. It's not just ozone, for example. We are exposed to multiple things, and they interact, and the response that we have from a health perspective is quite different depending on the combination of exposure. Very difficult to replicate in a lab, but as I'll show you, we are making attempts to be able to do that, to study research. Next slide. So the current situation, or what has typically been the situation in studying pollution effects on health, is shown here. There are multiple sectors interested in this problem. People look at the clinical response. People are looking at the biological response at the level of cells. There's technology development. So engineers are working on designing new biofuels and new ways of combusting existing fuels. And I guess missing from this would be a circle for toxicologists as well. And so what our goal in developing the lab that I'm going to tell you about called AirSafe is to bring that together. So what we're envisioning is the scenario on the right, where these sectors are integrated and they're actually talking to each other, feeding off of each other. And we look at combined exposures, not individual exposures. And at the center of that diagram, you'll see I've highlighted stakeholder groups. And this is a vision we've had to have stakeholders such as yourself, the people on this call today, help work with us, understand what we can do, but also help us understand the questions that are most germane to you so that we may be able to design research projects to give you answers for real world issues. Next slide. So we are building a facility called AirSafe, in which case we're integrating the research capacity from a very interdisciplinary view, which I'll show you, to try and meet real world needs that they're emerging as it relates to air quality and human health. So we'll establish this facility here in Winnipeg, and the goal is to really look at how air pollutants in combination contribute to affecting our health and disease as individuals and as a population. It's been a long haul. We started talking about this concept back in 2019. You go through a series of development steps, selection processes, you submit a grant, and then you find out a year later that you did or you did not get funding. In our case, we were delighted to receive this funding notification and the money in the bank, so to speak, in around March to July of 2024. So we've had the money for a couple of years. We're more than two-thirds of the way through completing the project in terms of its development, and it's about a $6 million touch with funds coming from multiple places. The chief funding from Canada Foundation for Innovation and Research Manitoba, an innovation fund arm, so they match. And then we've really had a lot of support from Children's Hospital Research Institute of Manitoba, the acronym there, CRIM, as well as from Manitoba Lung Association, which is a partner in helping us, will help us disseminate some of the information we develop. So we're really focused on four main areas, looking at the effects of indoor and outdoor air quality or air pollution rather, at the level of the cell and the lung. Keep in mind, we are lung researchers, but the lab is designed for people who are, for example, interested in cardiovascular disease to come in and take a look at what's happening there. So we can look at a very molecular and cellular level and complement that with studies in humans. So the lab that Chris showed you earlier is based at UBC. It's called APEL, APEL is the acronym. And so they are part of this whole process. And what we're able to do here in Winnipeg is understand why somebody may respond differently to certain air quality measures than somebody else. We can get down to the molecular level. We can even perform interventional studies to see if we can change the response. Those are not things you can do in living, breathing humans because of ethical reasons, obviously. So we study indoor and outdoor air pollution. We also have a large lab, and this is where Dr. Pascoe's work really is at the forefront, looking at recreational combustibles. So how does cigarette smoking, cannabis smoking, and e-cigarette use affect our lung health? And we can even look at whether they compound the effects of poor air quality if you're doing them at the same time. One of the things that I'll focus on for the rest of the 2 or 3 slides to follow is monitoring occupational air quality. We had a proposal to do that with Safe Work Manitoba. I'll walk through it in a second. So we'd love for this meeting really to be our first outreach to identify potential stakeholders who may want to be part of an advisory group to help us decide on the kind of research we can do that meets the needs or answers the questions in the industrial setting. At the end of the day, one of the things we really love to be able to deploy or is our evidence to develop and redefine public health tools. The AQHI, Dr. Pascoe talked about earlier, really based on a very severe outcome, mortality, but that's not the question we are getting today very often from example youth soccer leagues. Should we play at air quality index 7 versus air quality index 8 and why? So those are kind of best guesses at this point. We think we can help refine those tools. And from an occupational perspective, when is the right time to pull people indoors and off an outdoor work site if the air quality is suggesting that. Next slide. So this is encapsulates what AirSafe includes. I'm not going to go through it in huge detail here. We really have three main components. They have these acronyms, Accel and CAPE. Those are based here in Manitoba. CAPE in particular is a facility, which I'll show you a couple of pictures of in a second, where we're going to have a diesel engine and a customized biomass combustor, so we can generate the equivalent of a forest fire or the equivalent of a stubble fire. We can combine it with traffic-related air pollution, so the pollution coming out of the exhaust pipe of a diesel engine, mix it, combine it, measure it with very sophisticated air monitoring facilities, and then use very advanced control systems for exposures in human lung models. So we can take apart and then rebuild human lungs at a cellular level or even at a tissue level. We also make use of small animal models, mice, that can recapitulate these lung diseases like asthma or chronic obstructive pulmonary disease to ask what is happening and how particular elements in the air contribute to the disease presentation. The occupational air quality element of this, I want to come back to. We're really proposed to develop a stakeholder advisory group. We worked very closely with Michael Bolio from Safe Work Manitoba. He was one of our co-applicants. At that time, he was leading something called the Occupational Disease and Illness Prevention Strategy for Safe Work Manitoba, called ODIPS. And so the goal here was to actually purchase personal pumps, gas samplers for workers to wear at the work site, to sample the air so that we could then do very advanced chemical and particulate analysis downstream from that. That's still a goal. ODIPS has undergone, or SafeWork has undergone some changes at the top, and so it's a little unclear how we proceed in that way. Michael Bolio is still interested, but this is an area that I think we'd like to push forward on, regardless of whether ODIPS is the core of it or not, working with stakeholder groups. Manitoba Lung Association is working with us. They will help disseminate the information to the public and potentially to stakeholders like yourself when the time is right. Next slide. We have a series of labs. I won't go through them in detail. I've already talked about CAPE. That's the one at the top there. It's based here at the Bannatyne campus. I just want to point out that the recreational pollutant exposure facility is already built. It's functioning. We also have this advanced health and disease assessment suite, so we can do live animal testing. So these are mice. We can measure heart function, lung function, and do multiple other measures that are directly relevant to studies that are being done in human. We have a lab where we're developing abilities to burn alternate fuels in an efficient way, and we can actually test their effects on human human cells. And this is the lab that we will be studying or doing the analysis rather of the samples we collect from work sites. And then finally, I've mentioned APEL, the Air Pollution Exposure Lab based at UBC, where our colleague Dr. Carlson is doing human controlled exposures that are kind of guiding the way we do our own research. Next slide. So this is an example of one piece of equipment we've put in. On the left-hand side, it's a very deluxe exposure system. What you see on the far left is a metal box. It actually has wood shavings. So we ground up. This is work that Chris and his colleague Dr. Wu have done. They ground up wood pellets. You heat them up. They smolder, and smoke goes through a series of tubes. We can humidify it, cool it, and then this sort of metal box on the bottom is where we have human lung cell cultures that we can do exposures on. So what you're seeing in the top right is two videos of an individual airway in what we would call a lung slice from a mouse lung. So these are alive, and we can stimulate them with chemicals that cause the airways to constrict, much like an asthma attack, much like you would do if you were going for lung function testing. So the one on the left is a lung slice that was exposed to clean air only. And you can see it's kind of got this herky-jerky closing. It's just repeating over and over this movie. What's happening is we give more and more of this constrictor, and the airway gets smaller and smaller. If you do the very same study in a lung slice that was exposed to wood smoke for 1 hour, you see what happens. And what you should see is how much more narrow that airway gets with a single 1 hour exposure to wood smoke. So this is akin to a person who's worked outside in wildfire smoke. And if they already had underlying disease like asthma, you can appreciate here how this predisposes them to a greater constriction of the airways. And what that means is the air that you're bringing into your lungs and trying to breathe out, it's got to move through much smaller tubes. As you can appreciate, it makes it much more difficult to breathe. So this is just one example of the kind of things that we'll be able to do. I haven't touched on all the fun equipment we've got in the lab. This is one. Next slide. Thank you. So last slide, just to show you where we are. This is looking, I believe this is the 715. If I recall, is our street address 715 McDermott. That building on the left is the Chown building. The top floor where there's no windows is where we are building the exposure lab as we speak. I can actually look out my window and I can see a guy walking on the roof. I hope he's drilling a hole for a flue or something for us. It's under construction now, and we are hoping to be moving the equipment in there by December of this year and should be fully functional by January to February in that facility. In the building on the right, you can see Dr. Pascoe and I sitting in our offices there. That's where we have already established the recreational combustible exposure lab and the small animal pulmonary physiology labs. So we can connect, we can get from these two buildings through tunnels without going outside. So that's where we're located and where we'll be doing our work in the labs. Next slide. And then my final slide, just to remind you of what we're doing and the kinds of things we can do. We can do different exposures. We can look at disease risk by measuring molecular and cellular changes. We can examine ways of mitigating it. For example, we can put inline filters in our exposure facilities so we can see whether an N95 mask really is effective. And we'd love to work with stakeholders to help define really important experiments that we can do. And I'll just draw your attention to the far left of the slide where the occupational exposure is something that we built in from the beginning. We'd love to do. Our initial plan was to have these on-site air samplers. We have capacity to do very advanced analysis of the particulate and chemicals. And then because of the nature of the facilities we're building for exposures, we can, to a degree, recapitulate what we measure in the lab and really get a sense of whether or not particular chemicals or insults are at the root of some of the health problems that we may or may not be seeing in the workplace. And so we look forward to trying to develop concepts like that. And with that, that's it for me. I think the last slide's a thank you slide. Yeah. And we'll just leave it there for you.